You may be asking yourself that what is the largest star in the universe? Well, here are some of the stars and how big they are compared to the biggest star known in the universe. Point 1. Things that try to be stars. We begin our journey with Earth, not to learn anything, just to get a vague sense of scale. The smallest things that have some star-like properties are large gas giants or sub-brown dwarfs. For example, Jupiter, the most massive planet in the solar system. 11 times larger and 317 times more massive than Earth, and more or less made of the same stuff as our Sun. Just much, much less of it. The transition towards stars begins with brown dwarfs, failed stars that are a huge disappointment to their mums. They have between 13 and 95 times the mass of Jupiter. So even if we took 80 Jupiters and threw them at each other, although fun to watch, it wouldn't be enough to create a single star. Interestingly, adding lots of mass to a brown dwarf doesn't make it much bigger, just its insides denser. This increases the pressure in the core enough to make certain nuclear fusion reactions happen slowly and the object glow a little. So brown dwarfs are a sort of glowy gas giant that don't fit into any category very well. But we want to talk about stars, not failed wannabe stars, so let's move on. Main sequence. Once large gas balls pass a certain mass threshold, their cores become hot and dense enough to ignite. Hydrogen is fused to helium in their cores, releasing tremendous amounts of energy. Stars that do that are called main sequence stars. The more massive a main sequence star is, the hotter and brighter it burns and the shorter its life is. Once the hydrogen burning phase is over, stars grow. Up to a maximum of 10 times the mass of Jupiter. Up to hundreds of thousands of times their original size. But these giant phases only last for a fraction of their lifespan. So we'll be comparing stars at drastically different stages in their lives. This doesn't make them less impressive, but maybe it's good to keep in mind that we'll be comparing babies to adults. Now back to the beginning. The smallest Rayel stars are red dwarfs, about 100 times the mass of Jupiter, barely massive enough to fuse. They are the only stars in the main sequence that don't grow once they die, but sort of fizzle out. Red dwarfs are by far the most abundant type in the universe. Because they burn their fuel very slowly, it lasts them up to 10 trillion years, 1,000 times the current age of the universe. For example, one of the closest stars to the universe is the red dwarf. The closest stars to Earth is a red dwarf star, Barnard star, but it shines too dimly to be seen without a telescope. It burns far hotter and brighter than red dwarfs, which reduces its lifetime to about 10 billion years. The Sun is 7 times more massive than Barnard star, but that makes it nearly 300 times brighter with twice its surface temperature. Let's go bigger. Small changes in mass produce enormous changes in a main sequence star. The brightest star in the night sky, Sirius, is 2 solar masses with a radius of 1.7 times that of the Sun. But its surface is nearly 9,000 degrees Celsius, making it shine 24 times brighter. Burning that hot reduces its total lifespan by 4 times to 2.4 billion years. Stars close to 10 times the mass of our Sun have surface temperatures near 24,000 degrees Celsius. Beta Centauri contains 2 of these massive stars, each shining with about 20,000 times the power of the Sun. That's a lot of power coming from something only 13 times larger, but they'll only burn for about 25 million years. Entire generations of these blue stars die in the time it takes the Sun to orbit the galaxy once. So is this the formula? The more massive, the larger the star? The most massive star that we know is ST 2-18. Or Stephenson 2-18. A red supergiant with a radius estimated to be about 2,150 times that of our Sun. While UY Scuti was long thought to be the largest. More recent studies have identified Stephenson 2-18 is even bigger. If ST 2-18 were at the center of our solar system, its outer layers would extend past Saturn's orbit. Subscription is free, all you'll need to do is to click that button. See you in the next one.